Yes, now I would like to show you through a simulation what uniformly accelerated linear motion looks like in general. Yes, the ball is moving, and the distance traveled in each regular time interval keeps getting longer. What do you think? Compared to here, this distance is longer, isn't it? Yes, in this way, when accelerating in the same direction as the motion, the distance that the ball, the object, travels in a fixed time gradually increases. Yes, this is what we call uniformly accelerated linear motion. Let us watch it one more time. Yes, the velocity keeps increasing more and more. Yes, it looks like this. Could you visualize it? Now let us think about this using a VT graph as well. Let us consider it. First, at time t equals 2, the initial velocity was plus 3, so the point representing this on the VT graph becomes plus 3 at 2, this point here. From here there is a constant acceleration a. Since this acceleration was positive, it means the velocity increases. Therefore, the velocity increases steadily upward from plus 3. And when the time becomes 4, the velocity becomes plus 7. Is that clear? Now let us try to find the distance when the velocity changes steadily like this, using the concept of area in the VT graph we discussed earlier. In this case, since it is the area below the graph, we need to calculate the area of this trapezoidal shape. Let us shade this area. Yes, it becomes the area of this part. So this width is 4 minus 2, which is 2, and this height is 3. And since this height becomes 7, we can immediately calculate the area of this trapezoidal part. Yes, it becomes 10. Yes, in this uniformly accelerated linear motion, we can calculate that the distance traveled was 10 meters in this way. Is that clear? Yes, now actually this VT graph contains another very important piece of information. That is, in this uniformly accelerated linear motion graph, the line slopes upward to the right with a constant slope. Let us calculate this slope. Now what will it be? Yes, the change in the horizontal axis, that is, the change in time is 4 minus 2, which is 2 seconds. And the change in the vertical axis, that is, the change in velocity, becomes plus 7 minus plus 3, which is plus 4. Here let us simply write it as 7 minus 3. Then this becomes plus 2, which completely matches the acceleration value we found earlier. Is that clear? In other words, we have found that the slope of the VT graph represents the acceleration of the object's motion. Yes, is that clear? To summarize, in a VT graph, the area represents distance and the slope represents acceleration. This is not only a very important clue for deriving the 3 formulas related to uniformly accelerated linear motion later, but it also becomes a very important perspective when analyzing various complex motions. Is that understood? Yes, now let us summarize today's lecture. First, we learned to represent change using this triangular symbol, the delta symbol. Specifically, the change in coordinates, which we call displacement, can be written as delta x like this. And change is defined as subtracting the earlier quantity from the later quantity in time. Therefore, displacement becomes the final coordinate minus the initial coordinate. Is that clear? Yes, that is how it works. And along with this, we were able to define velocity. Velocity is the value of displacement over a time interval. In other words, it is displacement divided by time. Using symbols, we could write this as delta x divided by delta t. Furthermore, we call the quantity that represents how much velocity changes per second acceleration. Yes, this becomes the change in velocity divided by time. Yes, and if we express this using symbols, yes, we could write it as delta v divided by delta t. Furthermore, we learned that this can also be determined from a VT graph. Yes, the slope of the VT graph tells us the acceleration information. Is that clear? Yes, and we called the quantity obtained by removing the sign from these quantities containing directional information, namely displacement, velocity, and acceleration, magnitude. Yes, removing the sign is important. In other words, signs play a very important role in physics, and these signs represent direction. Is that clear? Yes, signs represent direction. We must never forget this. Is that understood? Now we call the quantity obtained by removing the sign from displacement distance. Also, we could determine this distance from the area of a VT graph. Yes, this was also an important point. Is that clear? And we called the magnitude of velocity speed. Furthermore, we called the magnitude of acceleration the magnitude of acceleration. Is that clear? Let us firmly recognize that these quantities, distance, speed, and magnitude of acceleration, are incomplete information that does not include directional information or signs. Is that understood? Yes. Now this concludes today's lecture. Thank you for your attention.